Okay, welcome back everyone. Hope you're feeling sufficiently caffeinated. This morning we have two very exciting talks, the first of which will be presented by Juliana Furgala from MIT Lincoln Labs, who will be talking about Magnetite, Rust-based OS services for seL4.
Hello everyone, as I was introduced, my name is Juliana and I'm here today from MIT Lincoln Laboratory to talk to you about an operating system that we developed called Magnetite, a secure embedded operating system that focuses on performance, isolation, and is, as you'll see familiar here, using seL4 as a foundational piece. So without further ado, let's jump in. Embedded systems are everywhere. This includes devices that people commonly don't think of as embedded, or think of as having a computer. For example, things like smartwatches, cars, and smart home devices. This also includes devices that the Department of Defense, or DoD, is concerned about, such as satellite communication terminals, UAVs, and weapon systems. Large systems like ships or submarines will often have independent or individual, a series of systems, embedded devices that allow them to function properly. Further, it's not just DoD-owned devices that are of concern here. The Department of Defense and the general public are beholden to systems beyond their control. For example, think power systems, common utilities, in order to continue everyday life. So why do we care that these embedded systems are everywhere? Well, it turns out that the picture surrounding them for security isn't a great one. We have seen embedded devices increasingly come under attack from both nation-state actors and criminal enterprises. This includes the Viasat satellite attack by Russia before they invaded Ukraine. This includes a hacker who tried to poison a city water supply in Florida. This includes malware that is targeted at critical infrastructure. This includes a disruption to public transit. And of course, it includes the famous 2020 example of the Colonial Pipeline hack, which took down a major US oil supplier. And lest you think that the DoD is somehow doing better than the rest of the world, well, the GAO wrote a report on the weapon systems that it looked at, finding that they were ripe with vulnerabilities that the DoD was only just beginning to understand the scale of. And unfortunately, in 2021, when they did a follow-up, they found that there continued to be significant gaps in cybersecurity guidelines. So why is this the case? Why do we see this seemingly unending stream of vulnerabilities in embedded devices? Well, to figure that out, let's look at a notional diagram of an embedded device. So this diagram illustrates a typical embedded device. You'll see an onboard computer on which there are layers of software running on top of it. And we're going to work our way here from the top down, starting with the payload and mission software. The payload and mission software, or you can think of this as the user application as well, is intended to carry out the actual mission, service, etc. Of this device. It's typically written by the application or mission owner or some contractor who was hired to do this job. It is very well vetted because at the end of the day, this is what clients are going to interact with, but it's not safety critical in itself. Then we have system control software. This is often supplied by the bus vendor and includes things like communication or navigation for devices like satellites, UAVs, drones. And this is typically supplied by the vendor along with the platform. So you can think of a drone as an example of this. Going one step further down, we have platform support. Likely you're all familiar with this. Includes things like drivers, hardware configuration, and is also often supplied by the bus vendor or the hardware vendor. This becomes increasingly privileged and also, unfortunately, difficult to test. Now, at the very bottom of all of these software layers is the operating system, which is Well, we have good representation in this room of operating system developers. But usually, this is developed by a third party who isn't aware of the application that's ultimately running on it and being provided to users. That means it wasn't developed with this in mind, and it's a large, complex piece of software that is responsible for providing all of those nice, featureful resources and APIs that the applications run on, and yet, yeah, it's unaware of the existence of the mission owner. So what should we take away from all of this? Well, the first thing is that there are several sources of software that are often running on an embedded device with various levels of trust. The second is that there's a sort of scale that exists with a easier to assure and audit in smaller pieces with less power to affect the system to more difficult to assure and audit with a great deal of power to affect the system. And in that latter category, we find operating systems. So that's why we've chosen to focus on building a secure operating system when we look at this problem of embedded systems and their security. However, there are a couple of challenges that make building a secure operating system difficult. The first one is incorrectness. As I mentioned before, operating systems are very complex. They, at least the traditional publicly available past ones, often have millions of lines of code and have regularly introduced features, several daily commits at least, constant changes that are hard to keep up with. And they have this complex job of trying to maintain a featureful set of abstractions for applications while trying to eke out performance, and this inevitably leads to bugs. It is also a requirement to use a low-level language that doesn't require a language runtime under it. For the longest time, this space was occupied solely by C and C++, which, among some of its downsides, doesn't have memory safety. Fortunately, Rust has come up in the recent years, but C and C++ remain quite prominent, especially in legacy systems. And Microsoft reported that 70% of their CVEs had to do with memory safety issues, and had been for the last decade. The second challenge that I'd like to talk about is handling compromise. We've seen that operating systems are complex. I'm kind of preaching to the choir about that. But existing systems often take a monolithic design that allows for easy privilege escalation. That's because all of these components are part of the same binary blob, and once one is compromised, it can be used to traverse or move through the system. So something like, say, a CPU temperature driver can be used as an entry point to manipulate the networking stack, for example, or even the scheduler. And also there's the fact that operating systems are the foundation for the applications that run on top of them. That means once an application is running on an operating system, it's trusting that operating system. So if you compromise an operating system, at least in this monolithic design, you can use the fact that these operating systems maintain application permissions and modify whatever is running on top of it. Your applications are no longer secure and are no longer guaranteed to run functionally correctly at all. So we've seen that these are difficult challenges, but we're not the first to see it. I'm in a room full of people who have been considering these same issues. So what are some responses that have been employed for existing operating systems? Well, the first one is patching. Patching is great. It is vital in ensuring that the systems that we develop are continually evolving in a positive way. However, well, that's kind of putting a Band-Aid on it. It mitigates the specific problems that we find, but it doesn't solve the original issue of why these problems come up. For example, lack of memory-safe language or just really complex software. There's testing in the form of manual or automated varieties here. These are quite helpful. However, it turns out that people, as Gage said yesterday, are really bad at figuring out test cases and finding bugs. It's tough. Then we have fuzzing and static analysis. Fuzzing being throwing essentially random input until something crashes to see if you might be able to detect the presence of a bug. Static analysis looking at the code itself and seeing are there some kind of common patterns here that might indicate the presence of a bug. And these are helpful and have been employed on centuries of CPU time. However, despite the fact that they have, we still see these problems. So clearly it in itself is not an end-all solution. We have formal methods. Formal methods like the ones that underlie the proofs from seL4. These are extremely strong guarantees. The only real downside to this is that it's really labor intensive and it can be difficult to scale up, meaning that, as Gernot was mentioning before, splitting things into smaller pieces will make it easier to verify. But operating systems in themselves are not inherently, at least the way they're traditionally structured, conducive to this kind of verification. And then we have solutions that deal specifically with compromise mitigation, like microkernels and compartmentalization. The idea that if you can have this least privilege principle and reduce the capabilities or rights that something has access to, then you can prevent or at least minimize privilege escalation in your operating system. Now, this is a great concept. Past approaches have been difficult to retrofit. Often experimental and not great on performance. We've seen some great advances in seL4 in this space, but in the past, performance wasn't one of the concerns of some microkernels. So what we offer here is a solution we've developed in-house called Magnetite. It is a new operating system that uses seL4 as its foundational piece and then builds around it a suite of operating system services entirely in Rust. I'll skip over the description of seL4 because where I am. But Rust provides some nice novel static analysis at compilation time that allows you to both run on bare metal in that C and C++ traditional sweet spot, but also ensure that the code you're writing is going to be safe from these many of these traditional memory bugs. Again, 70% of what Microsoft identified as the cause of their CVEs. So we intentionally chose these two as the building blocks of our system. And we architected Magnetite specifically for security. There were three focuses that I'll be talking about a little bit later. One is that we wanted to minimize privilege, so apply the principle of least privilege where we could. We wanted to isolate and separate functionality into different components, smaller pieces. And we wanted to make it easy to reason about data flow in the system. So now I've covered the motivation for Magnetite, and now we'll look briefly at the technical foundations. I know we're relatively short on time, and you've probably seen a lot about this for both Magnetite, for both Rust and seL4. So I'll probably skim a little bit more through this section than I normally would. Just to reiterate on a point here that seL4 offers a series of excellent benefits, all listed on this slide, but took 30 person-years to actually verify the 9,000 lines of code. Which means that if we're looking at the scale of a full operating system, really the first step that you want to take is breaking this down into pieces, because a task like this for verification, if you're setting yourself up for success here, requires smaller pieces. Also, a shout out that this was used in DARPA Hackums, which the drone is actually present here. A fun DoD-related connection here. So how does seL4 fit into this larger picture? Well, seL4 provides that scheduling and isolation, but there are all of these other kinds of properties and resources, services that applications expect to have when they run. For example, file systems are nice. Having drivers for your platform, very helpful. Having a sense of time and support for things like user libraries, also very important. So there's a lot of space that Magnetite had to fill in these features that applications would need to run. And of course, the design of those features is critically important to ensuring that we maintained a relative level of assurance and security as we were building up this stack here. So a little bit on Rust, originally developed by Mozilla for use in Firefox, now used by some of the major tech giants here, and relies on a new form of static analysis at compilation time to provide some memory safety benefits. There's some other nice features here that I'm going to skim over because Rust has been mentioned a couple of times. But I would like to point out that the NSA, or National Security Agency, released an advisory on software memory safety, where they recommended that organizations start shifting over to using memory-safe languages. And Rust was one explicitly named example of that. So we've looked at some of the foundations briefly on which Magnetite is built. Now let's actually take a look at how it's architected. And then we'll take a look at its status afterwards. So at the bottom of this layer here, and we'll be working our way up, is seL4. On top of this, we have a root task that is responsible for setting up these operating system partitions that we call silos. After it has done so, using information provided to it in a configuration file, kind of similar to Crichton's manifest has been mentioned, if we want a comparison for mental image here, it will tear itself down after setting up these silos. Then, in each of these silos, we have a silo init, which contains our executable loader, and is responsible for bringing up all of the other processes in the silo. I should note that each of the colored boxes here represents a separate process. Isolation is of forefront in one of our concerns. So the first of these processes that are brought up by silo init are the system services, of which you can actually choose which ones in your configuration setup that you need for your application. You don't need to just inherit all of these services. You actually get to choose which pieces you include in your silo, minimizing the size and making sure that you don't have any unnecessary code there. Afterwards, it will also boot up any applications per what is configured in this file here. And these applications can use either we call legacy, or either a C-based API that we have or a Rust-based library that we have with equivalent functionality here in order to access the operating system resources and services that we developed. In purple as well, you'll see something called an escrow process. That's because we don't want to inherently trust the applications. Although we're trying to separate these silos and have whatever applications you as an application developer feel comfortable running in it, we don't actually want to trust that this application, either intentionally or unintentionally, might not become malicious. And so these escrow processes are responsible for holding some of these privileges of the application in escrow. So for example, an application would not be able to mess with its C space, move around capabilities to ensure that it couldn't be properly cleaned up and resources couldn't be reclaimed. Let's see. So now I'm going to highlight a couple of points of emphasis in our development, one of which is separate services here. I'll talk about time-bound trust, and then I'll also talk a little bit about reasoning on data flow. First here, we have separate services. As I've mentioned a couple of times now, our focus is on really ensuring that the principle of least privilege is followed in our design, breaking out parts of the system into different processes based on the functionality that it actually needs. That means that the networking functionality is in the network service. It means that the synchronization-related primitives, think like mutexes and semaphores, are in the synchronization service. It means that, for example, memory management is its own service. These are all building blocks of the larger system. This is intended to reduce the chance for privilege escalation, meaning that if something were to be compromised, you would really have to compromise every service that you needed in order to carry out some ultimate malicious activity. And as Gernot was pointing out yesterday in his presentation, it prevents compromise spread through the system. Now, this does have some challenges, things that need to be done well. For example, complex communication patterns are a result of having all of these different pieces, and an increase in the amount of message parsing, which in itself tends to be a bug-prone writing process. But we found a couple of solutions for that. One is, of course, when you're separating this functionality into its service, keep it in mind with the kind of functionality that each of those services will focus on. So by intentionally putting them in bins based on, say, these are synchronization primitives, you can ensure that that kind of functionality is going to all be within its service, minimizing the kind of call overhead. Also, we employed auto-generated parsing code. Meaning that by providing the kinds of arguments that would be needed in communication, the code itself would actually be generated on the fly, meaning that we don't need to worry about potential bugs being introduced at this phase. The next part, I believe a slide ended up being accidentally taken out, so I'll just kind of talk to it verbally here, which is bounded time trust. So the idea here is that you don't want to trust the application, sure, that's why you have the escrow processes, but you also don't want the application processes to actually have to trust the services all the time. So the services do not have access to the capabilities of these applications. If you need something that would require modification of this or association with those capabilities, the applications will actually pass those over to the services for temporary use for that particular call or calls. And after that point in time, they are not kept, meaning that these services don't have to be trusted in the long term, and that lack of trust goes both ways. And last, I'd like to mention bounded data flow. I believe Gage mentioned yesterday the idea of critical domains and needing to separate out functionality, ensuring that you don't have data flow between, let's say, different silos in your system. And that's some of the reasoning behind ensuring bounded data flow here. We intentionally provide shared nothing or isolated by default silos of functionality, where if you want to set up channels, they are explicitly set up as part of your configuration at build time. That means saying you want one silo to communicate with another, that's going to be done by the root task that you see in blue here. And after it sets up the silos and those communication channels, it's going to tear itself down, it'll exit, and that configuration after that point is going to be immutable, meaning a malicious attacker won't be able to set up new channels or new silos or modify the existing configuration because the root task no longer exists to do that. This is one point where I think we made a different decision than what I heard from Cry10 before. But the idea here being that you have a sense of security in that, sure, you can rebuild with a different configuration, but in your current run, this form is static and to make sure that you know data flow is not going to change mid-run. So where is Magnetite right now? Well, everything in green on this slide is completely implemented. You'll notice that the main gaps that we have are in our user interface and device driver support. That's mostly intentional. The user interface bit, it's because we are focusing on embedded systems where people might be accessing this, say, through terminals, for example, but they're not going to expect a full desktop kind of experience. Also, in terms of device drivers, that's an artifact of us having currently small, but not forever, a set of supported platforms. We're a relatively small development team, and we started off with the Zinc ZC702 with ARM-v7, and we're working our way out from here. But that was really the first platform that we started in trying to prove that this was all possible. And you'll see in comparison, in terms of lines of source code here, that it's much smaller than real-time Linux is. I think someone yesterday had asked me about the size of lines here, and I didn't have a full number off the top of my head, so here we are. Overall, Magnetite is a mature system that offers solid basic operating system functionality that applications might need, and we're continuing to try to mature that as time goes on here, including other platforms, device drivers, and some further features. So how does it actually hold up against one of the common alternatives? We took a look at real-time Linux, and found that overall, while doing some of these core benchmarks, Magnetite outperformed it in many cases. The green here is representative of which one required less cycles, so lower is better. In the worst case, Magnetite across the board had better CPU cycle performance. In the average case, it was a little bit mixed. Our timer latency and channel latency was indeed higher in the average case, but it is worth noting that given our specific use case of embedded systems here, the worst case performance is often the one that, say, a drone needs to consider to make sure that it doesn't fall out of the sky mid-flight. And we found that our numbers overall in cycle time were more consistent and reliable than that of Linux, including in that average case. So there was less flex, less what if, and it was more consistent. So we posed that Magnetite has a clear advantage for Linux in this case with those kinds of system requirements. So lastly, I'll look quickly at some of the applications for Magnetite, just broad strokes, and then I'll take some questions. So Magnetite could be very useful for high criticality embedded devices. We're thinking things that don't often have, for example, a GUI interface kind of look. We're thinking things that need strong requirements on information flow, ensuring that you have containment of your applications and isolation of the components within at multiple levels, both in terms of the silos, the applications running within them, and the processes that are actually within these silos as well. And we ensured performance, at least relative to real-time Linux, to make sure that it would be able to meet the real-time needs of some of these embedded devices. So some possible applications include things like UAVs, more generally put as UXVs, there's multiple kinds here, critical infrastructure, and hypervisors. And with that, we will wrap up. So Magnetite is a novel operating system built on seL4 and written in Rust. That emphasizes the principle of least privilege in ensuring that data flow is bounded, that performance is timely, that you can separate out concerns of functionality in your services, as well as the capabilities that any process has access to. All in the name of minimizing the effect of compromise and ensuring that you can effectively reason about what's actually going on in your system for data. Magnetite is mature and demonstrates the possibilities of, as we've seen here repeatedly, using seL4 as a foundation for a secure operating system. And with that, I will take questions.
Thank you, Juliana. Okay, Iho.
Hi. So you had the slide before about application areas and so on. I may have missed it, but have you implemented those kind of systems on Magnetite as well? Like, what kind of example systems have you built on it?
Sure. So we started off with NASA's core flight software because we were looking at some of those embedded types of systems I was talking about earlier that are of interest to the DoD. And we did manage to run a series of their applications on it. That said, we think it has broader implications. So we haven't tested it on any of those real possible applications, why they're mentioned possible, but we intentionally designed it so it would be able to be suitable for those kinds of uses. Yeah. Mm-hmm. Thank you.
You showed some performance micro benchmarks. Do you have any sort of I/O benchmarks and other macro benchmarks?
Yes, good question. The benchmarks here are micro benchmarks, not macro. Part of that is because we would have to port over some kind of application if we wanted something at more of like a macro scale that we were looking at to be able to test the effectiveness of this against, say, real-time Linux. And the only application that we ported over, as I mentioned at this point, was NASA CFS as a test run here. So we do not have the larger scale benchmarks at this point, but we do have a paper in the works that will hopefully introduce Magnetite in in more in-depth form and include some of those kinds of benchmarks. It's just an upcoming task for us. Yeah.
Okay, one more question.
You mentioned Rust, and excuse me. One of the benefits of using Rust is the memory safety.
Yes.
Another one is also the concurrency support. Does Magnetite do anything to marry up the concurrency benefits of Rust, the multi-threading, with? I know we're still waiting on the MCS kernel, but does it do anything to marry the concurrency capabilities of Rust with the threading in seL4?
Yeah, I appreciate that question. Our services are single-threaded. They do not use those concurrency features as of this point. Doesn't mean that we won't in the future, but we started off as having those services be single-threaded. Yeah.
Okay, great. I think that's all we've got time for.